Everything. Okay. Okay, so what we're covering now is random variate generation. And just to kind of recap a little bit, we peeled back the hood a little bit on random number generation, which are these uniform 0-1 guys. And that whole topic is a whole thing in and of itself. And hopefully I've convinced you to use a good random number generator if you have a choice, such as the Mersenne twister. And so for those on Python, it comes with the Mersenne twister. For those on Java, the Java one is, well, I won't say it's bad, but it's questionable. I mean, the Mersenne twister is kind of the Ferrari of random number generators. There are other really good ones too, but it seems to be the most popular one. That's the one that SimKit uses by default, although it has other options. Then we moved into random variate generation, which is how do you take these uniform 0-1 random variables and turn them into one with another distribution. And so we saw the first and most basic way to do that is the inverse transform method. And that involves taking the cumulative distribution function, which every random variable has, and then finding the functional inverse of that, and then taking our uniform and then plugging it into that functional inverse. And as you saw, for simple ones like the uniform distribution of an arbitrary lower and upper bound, that it's pretty intuitive. But even for something as simple as the triangle distribution that we saw, you wind up with something which is a little counterintuitive. In other words, you wind up with the square root of the uniform, and that sets off, thinking, okay, this is going to be nonlinear because the square root is a nonlinear function. And it is, except that the random variables it creates, if you create a histogram, as we saw, it turns out to look like a triangle with the shape of the PDF being linear. The takeaway from that is just that when it comes to probability, don't trust your intuition. Intuition is terrible, and studies have shown that. I mean, we're terrible at estimating probabilities. The mathematics of probability is a bit weird, at least for some. And so it's not terribly intuitive, and yet it is what it is. So, okay, so, and then last time I showed something called composition. And what composition is about is taking typically taking a PDF, a probability density function, and that has a shape that we don't quite know how to deal with, but then cutting it up into pieces. And if we know how to deal with the pieces, then we create what's called a mixture distribution. And the way to generate from that is to first pick one of the distributions at random and then generate just from that one. And that's a little counterintuitive too, because intuitively, at least if you're like me, intuitively, I want to actually generate from each one of them and add them up somehow. I mean, that's just what my intuition tells me. But like I said, like all people, my intuition is awful. So, and that's not what you do. You pick one at random and just generate from that one. And then it's the randomization that creates the mixture. And ultimately, as I showed last time, it actually creates the distribution that you want. So I'm going to finish with a slightly more complicated example. And okay, I've been frustrated with the little whiteboard thing they have. So I want to use something a little more powerful. Okay, so here's the distribution that I want. It's the shape of the PDF is a trapezoid. So okay, now actually zoom puts all of its. So all right, I'm going to draw the PDF. And the shape of the PDF is going to look something like this. And this is the PDF, probability density function. And like in terms of what the parameters are, it's got 4 parameters. I'll just call them A, B, C, and D. And what they are simply the locations on the horizontal axis where the shape of the function changes. So we have 3 shapes. It goes linear up to the top. It goes flat for a while and then comes back down in a linear fashion. So 3 guesses why this is called a trapezoid PDF. The PDF is a trapezoid. Okay. All right. So we want to generate from this. So, and because the functional forms are fairly simple, I mean, just linears and flat and everything, we could figure out, here's what it would take to use the inverse transform method. And it is absolutely possible. I'd have to figure out what the equation of all these 3 pieces are, figure out where the demarcation points are, then I'd have to integrate it to find the CDF, and then I'd have to invert the CDF to get the inverse CDF. Again, all of that is absolutely possible, but there's a principle of laziness that comes into play here, and laziness plus the composition method says, well, what I really have here is I really have 3 pieces. Oops. Keep doing. I have 3 pieces, and the 3 pieces are a right triangle, a rectangle, and a left triangle. And again, this is supposed to be a PDF. And the way that the composition works is that if I cut the PDF into these pieces, then it's the area under each of the pieces that form the weights. Because what's the property of the weights? That is, the mixture distribution has to be a probability mass function, which means the probabilities have to add up to 1. So if I can figure out what these probabilities are, then I mean, I know how to generate from each of these 3 pieces. This is a right triangle. We did that. This is an arbitrary uniform. We've done that. And this is a left triangle. I mean, I didn't do that in class, but it's in the book, and it's fairly straightforward. So what do we need to know in order to figure this out? Well, I mean, all I got these values over here, which they are what they are. So what do I need to find out to determine what these different probabilities are? There's one missing piece of data. I need to know the height exactly. And so so basically I need to know what this height is. So we'll call that H. But here's the thing is that now the kind of breaking it up into the pieces can actually help me determine that. Why? So here, let's make this a little bigger. Let's see what we got here. Let's maybe make it 24 points so everybody can see it. So I know that 1 has to be the sum of these 3 guys. should go away. Okay. All right. But each of the, if I know what the height, let's just call the height. I want to solve for the height actually. And so the height is going to be, well, P0 is going to be the area of a triangle, which is 1/2 the base times the height, which is h. The middle one is just going to be the base times the height. And then the third one is going to be, again, another 1/2 the base times the height. So 1/2 the base times the height. And all of that has to be, whoops, no, that's not h, that's 1. All of that has to be equal to 1. But notice there's an h everywhere. So if I factor out the h, then and multiply through, I get like minus a over 2. Oops, no minus. I get it plus, well, b over 2 minus a over 2 plus c minus b plus d over 2 minus c over 2. And then notice, so sorry, I got a b over 2 minus a b. I got a c and a minus c over 2. So, and so I basically have h minus a over 2 minus b over 2 plus c over 2 plus d over 2. And remember, this is, and so actually there's a 2 everywhere. This is actually equal to 1. And so if h is just going to be 1 over that, which is going to be 2 over minus a minus b plus c plus d. And so, by the way, then my is going to be this b minus a times the height, which is 2 over minus b minus a minus b plus c plus d, etc. And the 2's actually cancel out, so I get b minus a over this. Etc. And I do the same thing for each of the others. So, so what my method is, therefore, is I want to generate I'll have a u and a v, and those are both going to be uniform 0 to 1. And then, okay, so now if u is less than, okay, and I'll just, is P0, then V is equal to this guy, which is simply A plus B minus A times the square root of, oops, no, of V. Else if, now here's sort of the tricky thing you have to watch out for. We have to start adding them together. This will be sort of return by well. Okay, so if it's in the middle there, then I simply return C plus C minus B times V. Else I return the left guy, which is D minus C times the square root of our V. On. Okay. So in other words, what I can do is you know, in a way, kind of the decomposition kind of helps me figure out what's what. If all I have are just these values. So the trapezoid distribution, it has 4 parameters that are these guys. There are some constraints on it. Obviously, is it clear what the constraint is? That this quantity had better be positive. As long as this quantity is positive, then we're good. So there are going to be sets of parameters that aren't going to work just because you can't create a genuine PDF from that. Okay, so I mean, and I wanted to kind of work this out just to kind of show you that I mean, if you want to, because on the next slide, I had kind of worked it out already, but just to hopefully this will kind of summarize what I did. Hopefully I did it correctly. So I might want to double check that, but
So,
yes,
so in the past, when you just showed it, you were generating 2 random variables.
correct.
2 random variables. This slide seems to be saying you can use the same uniform random variable to determine the probability and plug it into the return. Is that's is or is not?
Oh, it is seems to be up. That is actually incorrect. Thank you. This should be the Y here. Thanks for pointing that out.
And it wouldn't necessarily be Y equal.
Yeah, no, it's, yeah, I don't know what I was thinking on this. I know I was thinking of 2 things at once, and okay, so there's the correct. Yeah, we're and the thing is that okay, so I want to move on to the last method right now. It's for I don't know what I was going on. And okay, so this is fairly a little more complicated, but this turns out to be a useful distribution for what we're going to be looking at next. Just to kind of, just because if your intuition, unless your intuition is better than mine, it's still a little sketchy. I mean, it should seem a little weird. And for me, the only thing that that helps solidify it is to actually implement it, generate a bunch, and show a histogram. Because, mathematically, you can actually show this, but unfortunately, I mean, even though, I mean, I'm familiar with the mathematics of it, even though I don't always write the slide correctly. It's still, for some reason, mathematics isn't intuitive to anybody that I know of. Okay. So, so what I will do is I'll implement this and then just kind of show that it works. And I'll implement it correctly, not the incorrect one. But yeah, you had a very good point. You can't use the same random number for both. Although there's a trick that people used to use, which is to, if you want to use the same one, you have to kind of rescale it. In other words, in this range here, you actually have something that's uniform between 0 and P naught. And so if you want to, you can use the same uniform, but you have to divide it by P naught here. That was something that people used to do. Back when computers were tiny, I mean, physically big, but logically tiny. And so they were trying to squeeze out every last little cycle. These days, just generate a new one. Okay, so that's the composition method. And now, okay, so now for something really weird. And that's the acceptance rejection method. I don't know if this is true or not, but legend has it that this has actually been attributed to von Neumann. You know who von Neumann was, right? No. Google it. He's sort of a, let's see, do you take a class in like linear programming anymore? Evidently not. No. Okay. No. Von Neumann was a really smart guy back in the day. So just so you know. Anyway, so for some distributions, we're still kind of stuck. Why? Because even the composition method relies on the fact that we can cut it into pieces and deal with the pieces. But there are some probability distributions, even some standard ones, where we can't use the inverse transform method. We can't even totally divide it into pieces and use the composition method. And so in those cases, well, we have two options. The generic option is what I'm about to show you, the acceptance rejection method. That's the generic option. For certain probability distributions, there are specialized methods that are just specific to that one thing. So just know that those are the two choices. But if you only sort of get one, and in this case, I've sort of chosen these three generic methods. With these three generic methods, I have found that every distribution that I've encountered can be done using one of these. Now, that doesn't mean it's the most efficient one, but it gets the job done. And the purpose of this is so that whenever you need to generate a random variable of a particular distribution, you have the tools to do it. And after this, you will. Albeit not necessarily, sometimes there are these specialized methods that are super efficient or whatever. But okay, so here's the idea. And so let's start with a sort of a simple PDF. So here's one that looks kind of like a parabola. The blue is the PDF, probability density function. And the idea is to define something called a majorizing function. Now this is a function which is not a PDF, but it is it majorizes the PDF. Now, what does majorize mean? It doesn't mean that you've been promoted from captain or anything. It means that the function is totally over the PDF. And the idea is that the majorizing function is a simpler form, has a simpler structure, but is totally above the other. And that's a critical piece of it. So in other words, so our majoring function, which I call T for, I think, historical reasons, that's kind of what they've called it. So there are two properties that our majorizing function has to have. It has to, well, first majorize our PDF, meaning that it's bigger. And then the second piece, and this is kind of important too, that it have a finite area. In other words, if I integrate my majorizing function, I get some value which is finite. That's important. Because if we take our majorizing function and we divide it by the area under its curve, what do we get? We get a function which is finite and has well, I mean, the function itself doesn't have to be finite, but we have a function whose area is 1. And if I have any function which is always non-negative and has an area of 1, then that defines the PDF of some random variable. Does that make sense? So, and in this particular case, notice that for this blue PDF, I was able to define a majorizing function that's a trapezoid. And so now that we can generate from trapezoids, I can now apply the method. So here's the idea, is that I generate, well, and I choose a majorizing function in such a way that when I turn it into a PDF, it's actually something I know how to generate from. In other words, it's kind of a simpler form. In this case, I don't know how to generate from this blue thing, but I do know how to generate from this red thing once I turn it into a PDF. And so the method is so the final property of a majorizing function is that when I divide by its area, I get a PDF that I know how to generate from. And at least for random variables with a finite domain and range, I can choose from things like I can just actually choose a uniform, or I can choose a in other words, the simple ones that we've been working on, I can use as the basis for generating these. Okay, so so this thing is a PDF I know how to generate from. So my first step is I'm going to generate from it. But then here's the thing: if I don't do anything else, and then I'm going to get something that's going to be in the shape of a trapezoid. But I don't want a trapezoid. I want one of these guys. And that's where I generate a second random variable that's simply uniform 0 to 1. And I keep doing that. Oops, this should be a little f. Okay, so basically, so here's the idea. I generate from, let's say that the y that I generate from is right there. Okay, so it could be anywhere here. Let's sort of pick that one. And the thing is that now, this is the height of my majorizing function. So this is this point right here. Well, wherever that is, that would be f at y. If I were to kind of, and then this point here would be, I'm sorry, this is t of y. Not t over c, t of y. And this would be f of y. And so the idea is that the ratio of these two, because this is a majorizing function, that ratio is always going to be between 0 and 1. And so if my uniform winds up here, then I'm going to reject it and start all over. But if my uniform winds up in this region, I'm going to accept it and say, okay, I got one. In other words, the idea, like one way of imagining this, is that if I'm carving something, then first I'm going to sort of maybe take a chainsaw and rough cut it, so I can kind of chainsaw this thing. But then I want to kind of take like a chisel or something finer and cut away the pieces that are still left. In other words, the majorizing function approximates the shape, but then the acceptance rejection piece kind of carves away the extra little things that aren't there. And that now this area under the majorizing function, turned to C, it turns out that 1 over that is actually the probability of accepting. And show this mathematically. I don't know if I do or not, but that's and that probability of accepting, that's sometimes called the efficiency of the method. In other words, ideally, I want a method which the higher the efficiency, the more of these majorizing guys that I generate from I'm accepting. So if I have an efficiency that's low, then I'm kind of throwing away most of the stuff that I'm doing. And if I have one that's high, then everything else being equal, you want one that's high. And a high efficiency generally means that the majorizing function is a fairly close approximation of your probability density function. So here's a simple example. So, and this is now, have you heard of the beta distribution? No? You heard of it, yeah. So, the general beta distribution is it looks something like this. It's actually 1 over the beta function. It has 2 parameters, alpha and beta. There's something called a beta function, and then x to the alpha minus 1, 1 minus x to the beta minus 1. That's the general form, and that's for x's between 0 and 1. For the beta function is actually the integral of this guy from 0 to 1. Okay, so a beta 3, 1, actually, if we sort of plug into this, we see that alpha is 3, that turns it into x squared, and beta is 1, that makes it 0. And so it's something x squared, and it turns out that the beta function at 3 and 1 turns out to be 3. Okay, so that kind of looks like this. It's a square. And now we can actually use the inverse transform for this, of course, right? So, but since we're talking about the acceptance rejection method, here's a triangle majorizing function. We could also use, by the way, and this is often sort of a place to start. We could use a majorizing function. This majorizing function would simply be 3. And it would have to be 3 or greater in order to majorize this function. So the maximum is at the endpoint of 1. Plug 1 in, we get 3. And so this is kind of the best uniform one we could do. And in fact, the area under this uniform, the area is clearly 3, right? So the efficiency is 1/3. That means that we're throwing away 2 out of every 3 variables that we generate. Okay, and the technical term for that is that it sucks. So, okay, so you say, well, let's do a triangle. So can we do if we do a triangle, that's going to be a little bit better. So it should be. Let's see. So what is the function of this? Well, it's going to be, we go from 0 to 3. For a line, all I need is the slope. So rise over run. Rise is 3, run is 1. So my majorizing function is 3 times x. And for that, well, I can do the integral if you want. Sometimes you need that, or it's 1/2 base times the height, which is 3/2. So now, if I divide by that, then I have a triangle PDF. So now here's where you have to kind of keep things a little straight. So this is going to be a triangle PDF. That is, and it's going to be 2 times x is going to be what that is. But then what I want to do is that when I do the ratio of the PDF to the majorizing function, I go back to the original form. So I have 3x squared over 3x, and it's simply x. So I'm going to generate, well, a u and a v uniform, and then but I'm going to set y equal to the square root of u, say, and I'm going to do all that while u is greater than y. So where did the y come from? It came from the fact that this is the ratio. So plugging in y to the ratio simply gives me y. And so this method will return these. And so the efficiency, what is the efficiency of this? Well, it's going to be 1 over c, which is 2/3. So just by doing this, we've kind of doubled our efficiency, which kind of makes sense because the area of the triangle is 1/2 the area of the rectangle. So what this is the triangle. Remember, okay, so we're generating from this distribution. And remember that when we generated using the inverse transform method, we would have the square root of u times b, but here b is 1. Okay, so we're kind of leveraging the distributions that we've already done. Okay, well, let me talk a little. I think we've done a little bit of this, but so in terms of implementation, okay, so and this is for the SimKit version, we extend random variate base, or we implement random variate, and we apply whatever parameters we have. And the key is that this would go into the generate method. So at the time, do I? I think I have time to do the Java version. I'll do the Python version in a separate one. Okay, so here let's do I'll call it data 3.1 variate. I'll do what I just did, and oops, I forgot to extend. It's okay.
And
Sir, we can't see what you're sharing.
Oh, okay. Thanks. Sorry, forgot to. All right. So can you see it now? I'll start again.
Yes, thanks.
And let's extend. And okay, now since we're hard coding in what the distributions were, we don't have anything to set. And our parameters are. Okay, but now I want to okay, so for the it's I'm just simply going to follow. Um, um, sorry, I have to. Okay, so I'm going to say y is equal to the square root of what did I say? V. And I'm going to do all that while u is bigger than y. And then return y. Oops, what did I? Oh, I did it in the wrong place. It's not going to be initialized or something. I don't know. Java was kind of sometimes overly anal. No. So I have to put this under here. So let's make all these NANs. All right. Okay. So that's so I draw U, I draw V, Y is just the that guy. And then let's compile it. And then let's so it's in a different package. So base on random variable factory. Search package MV here 2 random. That's so we can don't necessarily need this, or if I give it the fully qualified name, but I'm lazy, I don't want to do that. Right. So Make sure we found it. That's all I'm looking for. All right. And then generate a bunch. Oh, and let's oh, where should we put it? No, we want um okay, so let's just okay, we got the numbers there. So I have 4 minutes to see whether it actually worked. Where you located, you are in. Okay. And that's Instagram of this. Hopefully it worked. Let's see. Okay, so as that looks pretty good. Notice that it kind of peaks at about 3. So so that actually did it. Now the thing about, oops, yeah, you didn't see that, did you? Okay, so let's do that again. Just for those, I then put it into R, which, you kind of use your favorite thing. I just find this to be easy to use. And so when I do a histogram, you can definitely see the curve there. You can see that it looks approximately like that. To strictly do it, of course, you would have to do something like a goodness of fit test to statistically show that this is that. But frankly, if you screw this up, if you make a mistake somewhere, it just looks totally weird. So that's that. Okay. So that's that. And I'm going to do some more examples on this tomorrow, and then we're going to kind of move to the next and final topic of the class. And also now I've been working on I've been doing my best to try to make sure that the write-up is actually correct, and so that's kind of be forthcoming. But in the meantime, you should have enough to do the written assignment that I posted this morning.